Hello everyone, welcome to the basic principles of nuclear magnetic resonance spectroscopy or NMR spectroscopy. For a proton, we discussed in the last lecture that in presence of an external magnetic field, the Zeeman splitting of nuclear spin angular momentum energy levels occur, and by the application of a radio frequency with frequency G, which is delta E by H, it is the energy gap divided by H, Gn beta and Bz by H. There is flipping of spin which leads to the record of NMR spectrum. Since we are concerned about mainly protons, this spectroscopy is also called proton magnetic resonance spectroscopy or PMR spectroscopy. In today's lecture, we will focus on NMR spectroscopy in detail. And for this, we are first looking into the experimental setup of an NMR. So let's say we have our sample here, the sample tube, and an external magnetic field, a strong, powerful electromagnet is applied using a magnetic field is applied using a magnet. And as we know, we need a radio frequency light source passing through the sample and a radio frequency detector. It will detect the light coming through the sample and is being recorded by a recorder or a computer. The frequency, radio frequency will be Gn beta and Bz by H. This equation has two parameters, the radio frequency and the magnetic field. So we can vary either the radio frequency or magnetic field. So the experiment can be performed in two different ways. Either the radio frequency is fixed or the magnetic field is fixed. Both these procedures give identical spectrum. In practice, it is preferable for most instruments to use a fixed frequency in the order of 60 MHz. We are fixing the radio frequency and varying the magnetic field in common experimental setup. The principle of this spectroscopy can be better understood by this figure. Here, the magnetic field is B0. Applied magnetic field is B0 and it's in this direction. At a particular magnetic field strength B1, this delta E1 will be the energy separation with values Gn, beta n and B1, you know. At B2, what will be the separation? Delta E2 and what will be a value Gn, beta n and beta 2. I am giving a higher magnetic field B3. The energy separation will be delta E3 and energy difference also Gn, beta n, B3. Now we are applying a radio. Here only there is the energy separation occurs, and to flip or excite the ground state spin to the upper state, we have to apply a radio frequency, and we are applying this frequency and the spin flips. But the energy needed to flip the spin corresponds to the energy gap delta E2. That much energy or that energy is enough to flip the spin from down spin to up spin or upspin to downspin, that is spin to downspin. That is, the energy gap at B2 matches with energy of radio frequency, and the proton will resonate at B0 equals B2. So, if the signal is plotted against magnetic field at the detector, the spectrum will be like this. This is for the absorption spectrum, and this will be the emission spectrum. That is, we can have either absorption spectrum or emission spectrum. The absorption spectrum measures the radio frequency getting absorbed by the sample, and the emission spectrum, there is a drop in the portion, that is, that much frequency is taken by the sample. We can plot any of these spectrum. Classically, the phenomenon of magnetic moment this phenomenon can also be understood by invoking Larmor precision. The term used in honor of British mathematician Joseph Larmor. A nucleus having a magnetic moment mu behaves as a bar magnet which spins on its axis. In the presence of an external magnetic field Bz, the interaction of mu with Bz produces a torque. This torque causes the mu to persist about Bz, as shown in this figure, and this phenomenon is known as Larmor precision, and the angular frequency of precision is referred to as Larmor frequency, which is omega, it is gamma into B0, depends on the intensity or the intensity of the magnetic field, amount of the magnetic field, where the gamma is called the gyromagnetic ratio, and it is defined as the ratio of nuclear magnetic moment and the nuclear spin angular momentum I into h by 2 pi. Here we are having a single proton, but in molecule there will be electron and chemical bond connecting to atom, and the precisional frequency, this Larmor precision, will depend on the chemical environment of the molecule. Consider two molecules, for example, methane and acetaldehyde. You know, both of these have same number of protons. Methane have 4 protons and 1 carbon. Here we are only considering protons. Since carbon is having a resultant spin 0 is NMR inactive, and only protons are considering. And here we can have, we are recording the proton NMR spectrum, we can have same 4 protons here. In both cases there are 4 protons, but their spectrum are different. You can see its spectrum is here only a single sharp line. Here we can see 2 spectral lines in the NMR spectrum of acetaldehyde. As a chemist, we all know the protons of acetaldehyde are not same like methane. How they are different? In acetaldehyde, there are methyl protons and the aldehyde protons. So in the case of a molecule, there will be a shifting precessional frequency of proton depending on the structure of molecule, and this gives rise to a term called chemical shift. Hence, the chemical shift is defined as the difference between the magnitudes of the magnetic field at which a free nucleus and a molecular nucleus resonate. It is in practice, one does not investigate the NMR spectra of a bare nucleus. Nuclei are essential parts of molecules held together by the electrons of the chemical bonds. It is thus clear that the electrons in a molecule affect the NMR frequency of a given nucleus in the molecule. The applied external magnetic field affects the motion of electrons also, which is surrounding the nuclei, thereby inducing a local magnetic field. That the electron induced a magnetic field in presence of the external magnetic field, not only the proton or nucleus, but also the electron will induce. This magnitude of local magnetic field is determined by the electron distribution around the nucleus. Hence, there is a difference in the magnitude of magnetic field for different nuclei. So, in methyl and acetaldehyde, this electron distribution makes different spectra. Now we are relating the local magnetic field B local experienced by a nucleus in a molecule to the applied magnetic field B0 by an equation B local equal to B0 into 1 minus sigma, where sigma is called the shielding constant or screening constant. The greater the shield by electron, sigma will be higher. So, the local magnetic field experienced by the molecule will be decreased, or nucleus will be decreased. Hence, this equation URF equal to Gn beta n B0 into 1 minus sigma by H can account for the chemical dissimilarity of the proton by this factor sigma. I will explain it with the help of the same acetaldehyde spectrum, NMR spectrum. Here, the peak position we have to note that you can see two peaks, and the peak position one corresponds to the magnetic field B1 and the other corresponds to magnetic field B2 as the magnetic field increases in this direction. Here you can also see that the peak, the intensity ratio of the peak this peak is nearly 3 times this peak, that is in the ratio 1:3. That is, the 1 is for the single aldehyde proton and the 3 is for the methyl proton. From this you can easily understand that the intensity of NMR signal depends on the number of protons in the molecule, or number of protons in the molecule, proton PMR spectrum. Then, how these two sets of protons resonate at two different magnetic fields? For the aldehyde proton, to the presence of this carbonyl group, the CH group is less shielded, that is, the electrons of this bond is pulled towards the carbonyl group or carbon, and so the proton is purely free, and it will be less shielded by the surrounding electrons. So it needs a lesser amount of magnetic field to make it resonate with the applied radio wave. But in the case of a methyl group, it is the 3 protons are highly shielded by the 3 CH bonded electrons. So it needs so the shielding constant is higher. The magnetic field experienced by the methyl proton is lesser, and so it needs more magnetic field to make the value or to resonate with the applied radio wave. It is for a constant frequency, that we are applying a constant frequency, as I already said, 60 megahertz in the common experimental setup. And so we need to increase the B local of methyl proton to make it resonate with the wave, radio wave at 60 megahertz frequency. Or we can say that for making a constant frequency, B1 into 1 minus sigma 1 will be equal to B2 into 1 minus sigma 2, or B1 by B2 equal to 1 minus sigma 2 by 1 minus sigma 1, as sigma 2 shielding constant of CH3 sigma 2 greater than sigma 1, B1 by B2 will be less than 1, or B1 will be less than B2. That is, the aldehyde proton will resonate at a lesser magnetic field than CH3 proton. This is what we have seen in the spectrum. Thus, B1 minus B2, the difference between the magnetic field experienced by the 2 sets of protons equal to B0 into sigma 2 minus sigma 1 only depends on the shielding constant, which is equal to B0 into delta, where delta is called the chemical shift of one nucleus with respect to other. In practice, we define the chemical shift of a sample as delta equal to magnetic field experienced by the sample minus magnetic field experienced by a reference compound divided by the applied magnetic field into 10 raised to 6 ppm. Generally, we are expressed it in parts per million. Since the magnetic field is proportional to frequency, you can also write delta equal to new sample minus new reference divided by applied frequency into 10 raised to 6 ppm. Here, which will be the reference compound we will take, that is, which is the tetramethylsilane, that is silicon having 4 equivalent methyl groups surrounding it. The structure of tetramethylsilane is this. The reason for using TMS, tetramethylsilane, as the reference compound is, the first one, it has 12 equivalent protons. The 3 into 4. So 12 protons are equivalent. That can be seen from this structure. Since all the protons are in the same environment, TMS gives a single intense sharp peak in its NMR spectrum. This is the first main reason which we are selecting TMS as the reference compound. Also, it has low boiling point and can be easily recovered after the spectrum is recorded. Next point is it is chemically inert. And the other most important point is the methyl group in TMS are highly shielded, that is, the sigma value is higher by the electrons. They are highly shielded from the external magnetic field. Consequently, TMS shows NMR at a very high magnetic field strength compared to other protons. No molecule would reach this tetramethylsilane. So it can be used as a reference. These reasons are very important why the tetramethylsilane is used as a reference compound in NMR spectroscopy. It is also to be mentioned that there are two chemical shift scales we are using to record NMR signal, which is delta scale and tau scale. Larger shielding means higher field is needed, or upfield or upfield shift. So we can again take the spectrum of acetaldehyde, and here I am taking this spectrum in the delta scale. You can see the delta scale, and it varies from 0 to 10 or 10 to 0. That is, on delta scale, delta is set equal to 0 for the reference compound TMS. This is the TMS peak for this. Delta is set as 0. As it is delta 0, it possesses the maximum shielding that we know. That is, the larger delta value means the proton undergoes a resonance at low field or down field, which implies a low shielding of nucleus. Delta value 0 means there is the maximum shielding, and from 0 to 10 the shielding decreases and it is changes to down field. It needs low magnetic field. That you can if you are plotting the magnetic field, it increases in this direction and the delta value decreases in this direction. Different we can use another scale, tau scale. Here is plot. Here you can see the two different peaks. The first on low delta value and the second on a higher delta value. That is, this undergo highly shielded proton, which is the methyl proton, and from the intensity itself you can realize this peak will be in the methyl peak. That is, it is having an average of 3 times higher. That is, this is the peak of aldehyde proton, and it is a downfield, or it needs lesser magnetic field, which gives a high delta value. We can use a tau scale also, such that tau equal to 10 minus delta. That is, those places where delta equal to 0, tau become 10, and those where delta equal to 10, where tau equal to 0. Now, delta scale is the internationally agreed scale to record NMR signal. Here we conclude this lecture. In the next lecture, we will see what information a molecule can give from NMR spectrum. Hope you understand the session. And thank you very much.